Yeah, so hello everyone. I hope you can hear me well. My name is Bernd Mohr. I will be the moderator here for this new webinar, which gets organized by the EU RISC2 project, which is a coordination project for coordinating HPC between Europe and Latin American countries. And we thought because of Corona, it's not as easy to travel. So this is why we do now basically started a new webinar. And as there's so many webinars already out there about programming MPI and OpenMP or something, we thought a topic like HPC systems and tools is not so much covered yet. And so this is basically the new series we will produce here in the next year. So there's more webinars coming up. You can go to our website. We have already scheduled one per month until the end of the year. And I will say something more about it at the end of the presentation. So I'm very happy that a few of you come here, and we will start our webinar series with an important topic, which everyone probably who works in HPC run into already, namely how to get scientific software installed in an easy way. And for that, we got a very great speaker, Kenneth Hoster from Ghent University. He is probably one of the very few experts in that field worldwide. He is working on it already for like more than 10 years. So he is a computer scientist and open source enthusiast from Belgium. He has a master and PhD in computer science, which he got from Ghent University. And since October 2010, he's a member of the HPC team at the Ghent University, where he's mainly responsible for user support and training. And as part of his job, he's also, meanwhile, the lead developer and release manager of EasyBuild, the topic of our today's webinar, and which is basically a software built-in installation framework for, mostly scientific software on high-performance computing systems. He's a very nice guy. So in his free time, he's a family guy and a fan of loud music, rock music, frequently attending gigs and festivals. He really enjoys helping people. I can say you from my own experience and sharing his expertise. He likes joking around, as you will see in the next 40 minutes, and he has a weak spot for stickers. So as I mentioned before, my name is Bernd Mohr, and I will be moderating this session. We want to keep that very interactive, so please, if you have any questions, type them into the chat, and that at the end of a session, we basically will have a question and answer session to answer that. Please keep your microphone muted so we don't have any background noises, and turn it only turn it on when we ask you to do that. The session will be recorded, and after the end, basically at some point, it will show up on our website. In the question and session at the end, if you are you don't want to type in a longer question, you can also use the raise hand emotion, and then we will basically call you to ask your question live. And with that, I stop sharing and I give the floor to Kenneth talking about EasyBuild.
Okay, thank you very much for the introduction, Bernd. The slides up that should be working now as expected, full screen. So again, thank you very much for the introduction. I had a slide to introduce myself, which I guess is mostly covered by now. Let me just summarize this, that I have indeed over 10 years of experience with, let's say, the fight of getting scientific software installed on HPC systems. using EasyBuild, working on EasyBuild, getting software installed is a big part of the job I do at Ghent University in Belgium. And I do like all the things that Bernd mentioned. I'm not sure he mentioned beer. So if you have an opportunity to buy me a beer, I will probably never say no. There's also a bunch of things I do not like. That definitely includes compiler errors, especially if it's a C++ compiler, and a whole bunch of build tools like CMake and SCons, Bazel, or complex software to install like TensorFlow and OpenFlow. And all of that grew out of the last 10 years that I've been fighting these things to get installed. If you want to contact me, my email address is on the top right of the slide. I'm also on Twitter. And if you want to interact with me through Slack, there's the EasyBuild Slack, which you can join as well. So feel free to do that if you have any questions on EasyBuild or if you want to reach out to me directly. So to the topic at hand, getting scientific software installed. As Bernd already mentioned, this is a big problem for lots of HPC sites around the world. Your supercomputer is essentially useless unless you have some scientific software installed on there. Many HPC sites provide a small or a bigger central software stack that includes lots of scientific packages as well. And providing that software stack is not easy. So it takes a lot of time, a lot of effort, especially on HPC systems, because there you really want to build the scientific software and all the dependencies that are required for it from source code. So you can optimize the installations for the hardware on which the software will be run. So the performance aspect of HPC is very important in this context. This puts a huge burden on either the researchers if they want to install the software themselves, or on the support teams if they want to provide some software centrally. Specifically for Ghent University, so looking at our support team, we get quite a bit of installation requests, probably because we're quite good at handling them as well. About 15% of the support tickets we get are related to software installation requests, but we spend way more than 50% of our time on handling those, even though we have EasyBuild. And up until recently, there was not a lot of collaboration between HPC sites. So each of them were just figuring out some way, either they had a dedicated person for it, or maybe a team who was installing software, usually manually by running commands manually, and they all had their own kind of system. And thankfully, thanks to tools like EasyBuild, this has changed over the years. So what's the big issue with scientific software? Why is it so special next to being installed on a complex system like a supercomputer? Well, the researchers who produce or develop this software really focus on the scientific problem that they want to solve. The software is just a tool for them. So they have to implement something to analyze their data or to make the simulation that they're interested in, but they're not really interested about the software development part of it. They're really interested in the scientific part, scientific aspect. So they don't really care to do standard things or follow good practices. As long as they can get something that works and they can push it out there and hope that it can be useful to other people, they are already quite happy. That leads to some specific aspects for scientific software, like non-standard build systems. So maybe they invent something themselves, or they have some fancy bash script that does all the installation and it works on their system, and they hope it can be useful for you. Versioning of the software, we see a lot of non-standard practices there, if there's any versioning at all. Lots of dependencies that people assume are on your system or are poorly documented. So what do you actually need for the application to work? Hard-coded parameters. We even sometimes see hard-coded home directories in make files, for example, which doesn't make any sense outside of your own laptop, and so on. So there's lots of aspects about scientific software that make it a bit special, and make it even harder to deal with together with being installed on an HPC system. So because of this, and sort of out of need, we created EasyBuild at Ghent University now well over 10 years ago. EasyBuild is a tool to get scientific software installed in an easy or easier way. And whenever we can, we do the compilation from source code. So if we can get the source code of the software, we really try hard to make sure we build it from source code and optimize it for the hardware on which it will be used. There's a strong focus on Linux and HPC systems. So on macOS, you probably will not get very far with EasyBuild because let's say the community is not really interested in macOS. There's a really strong focus on HPC, and of course to the performance of the software that EasyBuild installs. It's implemented in Python. For now, we still support Python 2.7. We're considering dropping that support in the near future, so the next couple of months or definitely the next year. We'll stop supporting Python 2.7 since it's a dead language. EasyBuild integrates with the more or less standard environment module system. So where you do module avail to check what's available, module load to activate software, and it generates whatever module files are needed for the software that EasyBuild installs. It's open source. It's available on the places you would expect on GitHub and the Python package index. And today it already supports over 2,700 software packages. That count does not include extensions. So that's things like Python packages, Perl modules, or libraries that you install on top of something else. We also support different compilers, GCC, Intel, and a whole bunch of different ones, and libraries for MPI, LAPACK, all of these things combined with those compilers. As I said, originally it was created in Ghent, but now it's really developed and supported by a community that's worldwide, and that's a very good thing. I'll share some more details about the features and how EasyBuild came to be over the years. If you've never used EasyBuild before, this is basically how you use it as an end user. So you have this EB command here, and you specify it in some way what you want to install. In this case, we're telling it, please use this file, file that specifies how to install version 2.7.1 of TensorFlow using a particular compiler toolchain and using, in this case, CUDA 11.4. You hit enter and EasyBuild opens this file, figures out what to do, and then actually goes ahead and does the installation. Now in practice, especially installing TensorFlow will take a lot longer than was shown here on the animation. But the key aspect here is that whenever you want to install something, and it is supported by EasyBuild, it's just the same operations you have to do over and over again. No matter whether it's TensorFlow or OpenFOAM or some other complex software package, EasyBuild knows how to install that from source, and so you don't have to worry about how that's being done exactly, at least if you don't want to. You can figure out what EasyBuild does if you really want to. So unfortunately, I don't have the time today to explain EasyBuild in depth, what it can do, how it works, how you can use it. So in the interest of time, I'm sticking to a high-level overview of the features here. So the main purpose of EasyBuild is to fully autonomously. So that means when you start, when you let it run, it just goes ahead and does the job by itself. You don't have to answer questions or interact with it. It builds the software and installs the software, mostly scientific software, and it does that from source. It also generates environment modules to give you access to those software installations. And it does it keeps a log file of what it was doing during the installation. So with which commands it was running, which output was generated by those commands, and so on. It's very useful to have later if you want to see how exactly something was installed. You can go and check later how that exactly was done. It's highly configurable. There's very little things in EasyBuild that are hard-coded. So if you want to make it do something different than it does by default, you usually can. And there's different ways of configuring EasyBuild through files, through environment variables, or through command line options. It's very actively developed. People are working on EasyBuild every day, basically. And we push out frequent, stable releases about once every 6 to 8 weeks. It's more going in the direction of 8 weeks now. But we definitely do multiple releases a year. There's a whole bunch of more specific things that EasyBuild can do. It has a plugin-like system, so you can actually tell it how to support additional software, even though it's not included in EasyBuild itself. You can see what it's doing by running it in a different mode, let's say. So it basically shows you more details about what's going on. Or you can ask it to give a high-level overview of which commands it would be running to do an installation without actually doing it. So that's very quick feedback you can get. You can customize it if there's some aspects of it you don't like and small things you want to change or customize according to your site's specific needs. You can do it as well by writing a small Python function that EasyBuild picks up whenever it has to. So you can actually manipulate the functionality along the way without rewriting the tool from scratch. behind the scenes, EasyBuild is following a couple of steps for every installation it does. So it starts with opening this what's called an easy config file that tells EasyBuild what to install, which version, using which dependencies, using which toolchain, and so on. So once it has parsed that easy config file, it knows what to do, and it will start with finding the source files or downloading them if it has to, unpacking them, maybe applying patch files, preparing the build environment, and then running the standard configure, build, and install steps, maybe with a test step in between after the build. When that is all working, it can also look into extensions like installing Python packages on top of it or R libraries, things like this. It usually does some kind of sanity check. So that means, are particular files in place in the installation, or is a simple command like --help actually working, just to make sure that we're not getting a totally broken installation and telling the researcher that it is installed. And then it cleans up, generates the environment module, and does some additional small steps at the end. So each installation is done through these steps, and how each of these steps are actually filled in. So what the configure step does, for example, is determined by an easy block. So that's like a Python script, and also what's specified in the easy config file through easy config parameters. So that's a bit high level, but maybe it gives you an idea of the structure that's behind the installations that EasyBuild does. So EasyBuild has been around for quite a long time already, over 10 years. Actually, it was created in 2009, in the summer of 2009, not by me, but by our current technical lead in HPCU Ghent, Steen de Weert. It started as an in-house project, so we were basically getting our first central HPC cluster in Ghent in 2009. We started getting lots of requests from researchers for software, and we realized that with a very small team back then, it was just 2 technical people, there was no way we would be able to keep up with installation requests unless we had some automation around this. That's why EasyBuild was created. Over the years, we slowly improved it, added support for more software. It was redesigned a couple of times by student interns as well, who have done a great job at that. And in 2012, so this year, it's 10 years ago, we have first released EasyBuild in the public. So by November 2012, so that was during the supercomputing conference, we released EasyBuild 1.0 because after some other people outside of the Ghent team were testing it, we felt it was stable enough, useful enough for others that we could declare it a useful tool for others as well. And then over the years, it slowly started growing. We actually only added proper documentation in 2014, pretty much on the demand of the community, the small community that was starting to grow around it. We also started doing what we called hackathons. So that was small sessions, about 10, 20 people, where we work together on improving EasyBuild in certain ways, or teaching others about how to use EasyBuild, how to improve it. That was done all over Europe, and in one session in Texas in the US as well. We also did quite a bit of promotion at supercomputing and at ISC, the European Supercomputing Conference. We did birds of a feather sessions called Getting Scientific Software Installed. These were not specific to EasyBuild alone. We talked about other tools there as well. But it did help us quite a bit to get the word out there and get other people to know about EasyBuild. Then over the years, when more and more people started using it, we realized we made some mistakes, or we wanted to make some backwards incompatible changes. And we tried to keep up with a proper versioning. So whenever you have a breaking change, you make sure it's a new major release. And we've done that a couple of times now over the years. We also added support for Cray systems, Cray systems are quite different from a regular supercomputer because they have a very specific software environment. And that allowed the people at CSCS in Switzerland to start using EasyBuild on their systems as well. EasyBuild 3.0, where we switched to LMOD as a default tool, and where we have some GitHub integration as well, which I'll briefly explain in a bit. What we also did is gradually moved from hackathons to user meetings because the community was getting bigger, and we felt we had to organize things a little bit differently, where people not only come to the meetings to learn about EasyBuild, but also show how they are using EasyBuild in their systems and let other people learn from that. The last two of these have been virtual. We're hoping to get back to a physical user meeting in 2023. EasyBuild 4.0 was the first version that supported Python 3, so running EasyBuild on top of Python 3, which was a very important thing to do, of course, since Python 2 is a dead end, essentially. So yeah, sometimes we have to do some development that doesn't help the actual functionality, but make sure that EasyBuild stays alive. And then also in the last couple of years, we've had actual tutorials at the ISC conference, so half-day tutorials, which has been very useful for, again, getting the word out, but also making sure that people understand the basics of EasyBuild, how it works and how they can use it in their context as well. And then last in this timeline, a little bit over a year and a half ago, EasyBuild was also selected as the software installation tool for Lumi, the big pre-exascale HPC system in Europe. And that was a very good result for us after over 10 years of hard work, that we see very big supercomputers also picking EasyBuild as their tool of choice. A little bit more about the EasyBuild tutorial. So it's quite extensive. It's half a day in ISC, but you can probably also give the same tutorial in a full day if you spend a little bit more time on the hands-on part. You can find it at easybuild.io/tutorial. It was presented at ISC 2020. Well, not really, because tutorials were canceled then, but we still did it online outside of the ISC conference. It did happen at ISC 21 in a virtual setting, and it was fully recorded. So you can check that recording. I think it's about 3 hours of material there. So you can work your way through it on your own pace. That's very good. The basic tutorial that we gave at ISC covers the real basics. So it assumes no prior knowledge about EasyBuild, and it covers all the terminology. So easy configs, easy blocks, and all these things. It explains what that means and how things fit together, how to install and configure EasyBuild, how to use it, and also how to do troubleshooting in case something goes wrong. There's lots of hands-on exercises in the tutorial as well, which is very useful if you're new to the tool. Like we deliberately give you things that are known to be broken, and then we ask you to try and fix it yourself. And that's very helpful to learn about how EasyBuild works and how to deal with the problems that you run into on a daily basis if you're using EasyBuild. We also did another tutorial for the Lumi support team, which was recorded, and that goes quite a bit further beyond the basics about implementing easy blocks and using hooks to customize EasyBuild and so on. And also all that material is available both on YouTube and in the tutorial website. So as I already mentioned, the EasyBuild community has grown quite a bit over the years, way beyond what we ever expected. It's basically used all over the world, and the best way we have found to figure out where it's being used is by looking at the map of documentation visits. So you can see it's being used in the US, also already a bit in South America, quite a bit in Europe and Asia, Australia, pretty much everywhere. And we have a worldwide team of maintainers as well. The EasyBuild user meetings have been really successful. Actually, the last physical one we had was in Barcelona with over 50 people attending. And we have also always supported remote participation. So we've been recording all presentations and doing live streaming. So even if you're not able to attend physically, you can definitely get the best out of it. And all the recordings of the presentations are also available on our YouTube channel. So we haven't started planning the next edition yet for 2023, but we hope to do that soon. And beyond the user meetings, we also have smaller dedicated sessions, tutorials for specific groups or specific sites. The picture shows a bunch of Cuban HPC system administrators who were visiting Ghent University last June, and where we did a small session like this to basically get them up to date with the latest developments in EasyBuild. So on demand, and if we have time for it, we can do dedicated sessions like this as well. If you want to get in touch with the EasyBuild community, you can do so via the EasyBuild Slack channel. I highly recommend this because it's very active. It has over 650 people, about 650 people there, and you basically can get around the clock support. It's people in the US, people in Asia, people in Europe. So whenever you have a question on EasyBuild, you can post it there, and it's quite likely you will get a good response. It's open for anyone to join, so just go to easybuild.io/join Slack. Then A very important feature in EasyBuild is the GitHub integration we have. So relatively soon after the public release of EasyBuild, about 3 years into the start of the EasyBuild community, we started getting lots of contributions, which is good. But it was also very difficult for us to keep up with those. Mostly because there was very little structure in the pull requests and the contributions we were getting. And it was also a growing number of different people who were doing this with different backgrounds. So that was a bit of a challenge. We already had a small team of EasyBuild maintainers there, but so it wasn't just us as HPC Ghent, it was other people helping out as well. But it was still a bit of a problem. Because of this, we implemented GitHub integration. So we basically let EasyBuild talk to Git and GitHub and let it do things for you, so you don't have to do it manually. And that includes things like testing pull requests that have been open, or actually creating pull requests, updating pull requests straight from the EasyBuild command line. So you don't have to run any Git commands. You don't have to click around on GitHub. You can let EasyBuild take care of that for you. That's very good because that basically means you're streamlining the contributions as well. Contributions look the same if EasyBuild does them automatically, and that's good for the people who are reviewing the contributions because they know that certain things don't have to be double checked if EasyBuild took care of that. This is very well documented as well. And to get the feeling across what this means, if you want to do a manual contribution to EasyBuild, so you have an easy-config file, one of these build recipes that you want to add into EasyBuild, the black box on top shows you all the commands that you would have to run manually. So you have to rename it to have it, make it have the correct name. You have to move it to the right place. Then you have to check out the develop branch, create a new branch from that, add your file there, do a commit, and then push it to GitHub. And then afterwards, you have to go to GitHub and click around to open the pull request and fill in some boxes like the PR title and maybe some message in the description and so on. And a lot of details you have to get right. All of that is basically now condensed into a single command, eb-new PR, and EasyBuild takes care of all of that for you. So you don't have to do it manually, and EasyBuild doesn't make mistakes when it does this. So it saves you a lot of time. If you're not familiar with Git or GitHub yet, you don't have to worry about that. EasyBuild knows how to do that. And even for people who are experienced with Git or GitHub, it's still a big time saver. So you don't have to do this dance of multiple commands. It takes care of the details for you. So that was implemented basically end of 2015. And by the middle of 2016, it was starting to be used quite well by the community, as you can see in the graph on the left. So the green part of the plot shows how many pull requests have been opened with the automation we have in EasyBuild versus how many were created manually. That's the red part. And you can see over the years, we're basically last year was about 90% of all pull requests for easy config files were opened with eb-new PR. That's very good. It's very helpful for maintainers. What's maybe not so good in some sense is that we're getting more and more contributions. So partially thanks to the automation, it's now a lot easier to make contributions, which also means we're getting more pull requests. So it does streamline things, but it does have the effect of even more contributions. I know you can also see the graph on the right shows the number of unique contributors per year. You can see that's also steadily growing, and we're now over 100 different people per year that make a pull request to EasyBuild. And that means you have to talk to lots of different people, hope that they have time if any changes need to be made and so on. So that puts quite a bit of demand on the EasyBuild maintainers. Another aspect that we see as well, partially thanks to the community contributions, is that the number of different software packages that EasyBuild supports is growing steadily. So we now have over 2,700 different software packages. So that doesn't include versions or different compiler toolchains or anything like this, or really different packages. And then if you include the extensions, you have to add about 2,000 more. That's quite a bit of different things to maintain and to keep supported. And this is only growing, so it's only getting worse in some sense. It's a pretty stable growth. Pretty stable upward trend, and it's not actually slowing down at all as far as we can see. That's good. EasyBuild supports more software, but it also means you have to maintain more things and have to be aware of more different software packages, which of course puts a bit of a burden on us as well. Now, this actually brings me to the next part of the presentation, where maybe this is a bit of a personal view, but I think these trends are pretty common, and lots of people in the HPC community are seeing them. We're seeing an explosion of the scientific software that people are using on HPC systems. And I think that's mainly for two reasons. And the biggest one is definitely that more scientific domains beyond the classical physics simulations are starting to use HPC systems. That definitely includes bioinformatics and artificial intelligence and machine learning. So different domains means different software, means more software, and we have to deal with all of these things. Yeah, wider adoption also of HPC, and then specifically of GPUs that we see, especially in AI, but also in bioinformatics, also leads to different software. Next to this, we also see increasing interest in cloud infrastructure, so especially commercial cloud like AWS and Azure, and resources like this. That does put a bit of a challenge on the people who use this as well, because the software that they typically get on the HPC system is not just available in the commercial cloud. So somehow you need to bridge that gap and figure out how you can get your software available there as well. If you have the necessary expertise to build it yourself, that's fine, but lots of people don't have that, and that causes a bit of trouble. We also see increasing variety in CPUs, so system architectures, basically Intel and AMD. Well, Intel was alone for a pretty long time in the HPC community. AMD is now back, and back pretty seriously. So lots of new systems are getting AMD CPUs. But we also see ARM coming up, and HPC power has never really been away, even though it's a small portion. And in the near future, we also see RISC-V, so the new type of open source CPU coming up, and quite fast. So this is the interest in this is growing quite fast. And this is only CPUs. Then we're also talking about GPUs. NVIDIA was the only real GPU for scientific computing out there for quite a long time. That's also changing with AMD GPUs, soon Intel GPUs coming up, and then other very specific accelerators like TPUs and IPUs are becoming relevant as well. So this is all exploding in our faces a bit, and we still have to deal with that. And unfortunately, the available manpower we get in HPC support teams isn't really growing. So we're still more or less the same number of people as we were 5 years ago, and we have to start dealing with this bigger mess of things in some sense. So we feel that EasyBuild is very helpful with this, so it automates a lot away of this pain, but it's probably not enough anymore. So we're collaborating together on a tool to make the installation of scientific software easier, but you still have to install the software yourself, and you may still run into problems that are very specific to your system. So even though EasyBuild is a big help, we see that HPCs are still spending quite a bit of time in getting the software installed that they need for their users. Especially for software that's not supported yet in EasyBuild, it can be quite a bit of an effort to get it properly supported in there. And that makes people maybe sidestep that and install it in other ways, which then doesn't help the EasyBuild community. So that's a bit of a problem. Small differences in the way your system is set up, or the way which OS packages you have installed, or how disks or partitions, like how big your /tmp directory is, can cause trouble with some builds that only some people see, not everybody sees. So that's not a good thing. So it's not this is definitely not a solved problem, and the situation is getting worse. We're getting more software, we're getting increasing variety in hardware, more accelerators, and all of this. So we see an opportunity for more collaboration beyond just EasyBuild. So basically collaborating more and maybe doing something a bit more centrally to tackle this problem in a better way. And it also goes beyond just getting the software installed, because that's actually only the first step. We would also like to be able to verify that what we install is actually correct. So is it actually producing valid scientific results? And very often we just don't have the time to do that. And we also want to check if the performance of those installations is actually how it should be. So if you're getting a 1 nanosecond per day speed of a GROMAC simulation, is that actually good for the system that you have, for the hardware that you have, or not? And does it stay like this over time, or does it maybe go down as you make changes to the system? So all of these things we would like to do, but we've never really found time to do that. The reframe tool that's being developed by CSCS is definitely a step in the right direction here, but there's more collaboration needed to work on this problem together. And that's where the EaSI project comes in. So EaSI is short for the European Environment for Scientific Software Installations. There's a clear link here between EasyBuild and EaSI. So it's called EaSI, not by accident, of course. So this is a new project, a collaborative project that sort of grew out of the EasyBuild community. So most people involved in this are also involved in EasyBuild, but it goes way beyond what we do with EasyBuild. The central idea of the EaSI project is to build a central stack of scientific software installation. So that's basically in one place that you can use anywhere, whether it's an HPC system or a personal laptop or a VM in the cloud, or it doesn't really matter. And it also shouldn't matter what type of Linux environment, whether it's Ubuntu or Fedora, which OS packages you have installed. So all of that shouldn't really matter, and you should be able to use the software installations we provide out of the box without doing anything special. Of course, again, there's a big focus on performance here, since this is intended for computational science. We want to automate as much things as possible. We want to test as much as we can, including performance, and we want to collaborate with as many people as we can. Now, explaining the EaSI project in detail is again something that's not enough time for in this talk. I can give a high-level overview of the project though, and then refer you to some more resources for more detailed information. So this slide is a high-level overview of the project. Okay, I lost my mouse, but it doesn't matter. It's a high-level overview of the project where you can see it's basically 3 layers. There's a file system layer, which is responsible for distributing the software installation, so making sure you can actually get it on your system. There's a compatibility layer in the middle, which makes sure that it doesn't really matter what kind of Linux distribution you have installed, whether it's Ubuntu or Fedora, or which packages you have installed in your OS. We mostly don't care about that because we take matters into our own hands with the compatibility layer. We, for example, provide our own glibc installation, and we use that rather than one in the operating system. So in some sense, this is very similar to what containers do, but we don't use containers. So we call this containers without the containing. And then on top, you have the software layer, and this is where the actual scientific software installations are, which are optimized for specific types of CPUs, whether it's an old or a newer Intel CPU, AMD Rome, AMD Milan. So we have separate software stacks for each of those types of CPUs. Our long-term goal is to not only support Intel and AMD, but also ARM, maybe also Power, although we see a declining interest in that. And in the near future, definitely also RISC-V. So whenever RISC-V systems are there and ready for HPC, we also want the software to be there already, so you can start playing with it straight away. All of this is heavily inspired by what the team at Compute Canada has been doing. So they have this central software stack that is being used across HPC systems and in Canada for several years already. What we do is pretty much the same thing. It's the same idea, but we are pulling it open not only to different types of CPUs, but also making it a community project. So people can help out, actively help out, and get software added into this software stack. This is a bit specific. This is basically the file system layer of EaSI. It's how the software is distributed. It basically boils down to having a central place. The Stratum 0 is like a central server. And then the Stratum 1s around that are essentially mirror servers. So they have a full copy of all the software we provide. And whenever you want to use the software that's provided in EaSI on, let's say, an HPC cluster, you use this certain VMFS software package, which is a special type of file system, essentially. As soon as you start accessing files in EaSI, they are automatically downloaded in the background, and you can start using the software as if it were available locally. Now, this is a bit difficult to explain, and the best way is actually to see it in action and to try it yourself. So we definitely recommend trying to use the EaSI pilot repository and getting a feel of how this works. What does all this mean? It basically means that to get access to all the software we have installed in EaSI, we provide through EaSI, you basically need to do two things. You need to make sure that CVMFS is installed and configured. So either you do that system-wide, which means you need root access or admin privileges on your system, or you can use a container, a Singularity container image that has everything installed in the container just to get access to EasyBuild. Once that's taken care of, you can set up your environment. That's done by sourcing an init script, which is the second line here. So you just source the init script that we provide in the Easy CVMFS repository. And that's enough to give access to all the software that we provide. So then you can start looking what's around there, doing a module avail. You will see TensorFlow, GROMACS, OpenFOAM, all these things will be there. You can load the corresponding module and straight start using the software. So really the only software package you install is CVMFS, and that's a portal that gives you access to all the richness that's available in Easy itself. I hope I can do a quick demo of that at the end of the talk. So once this is all set up and you have things working, this opens up a bunch of use cases. So the main one is getting a uniform software stack. So no matter whether you're running on your own HPC cluster or you're running in a VM in Azure or AWS or on your own laptop or server, you're basically getting the same software everywhere. And that's very attractive for researchers. You can even go beyond that. You can use the Easy software stack in a continuous integration environment, something like GitHub Actions, for example. If you're writing your own small software package and you want to run tests, but you need, let's say, 10 dependencies to get your software to work, you could just use the pre-installed dependencies from Easy and just only build your own thing on top of that. So you don't have to build all these dependencies yourself. They are just sitting there waiting for you to use. If you're doing HPC training, thanks to Easy, you can very easily set up a throwaway cluster. So you can set up a Slurm cluster in AWS, for example, that's temporary. And you won't have to install any scientific software on there if you use Easy. Everything will just be available straight away and will be compatible with the hardware that you're using. We also hope this will open up the door for collaboration with the scientific software developers themselves. So rather than us just installing the software and then throwing our hands up and say, look, this is the best we can do, and now you have to check and make sure it actually works as expected. We hope that we can get the actual developers of the software to take a look at how we install things and basically put on approval stamp on our installations. And that way other people that are just using those installations can benefit. This is only possible if you have something very centralized, because there's no way you can get the software developers to check every possible installation on all the HPC sites around the world. That's never going to work. But if you have something that's very central, then everybody's using, this certainly becomes possible. Then there's community software. So we want to let people add software into Easy and build workflows with that. So currently Easy is ongoing in some sense. It's still unfunded, so people are working on this on the side. There's no dedicated funding for it yet. That's going to change really soon because we actually have an approved EU project, which I can't give a lot of details on yet, but we expect this to start early 2023. So in the next couple of years, you will hopefully see a lot of activity around Easy, and this will become something that you can really start relying on for your scientific research. It's currently a work in progress. We have some stuff there that works just to show the concept and give you a feeling of how powerful this can be. We're also getting some help from AWS and Azure here. They're basically giving us free credits in their cloud to start building the software installations, testing things, and making sure everything is working. What we do already have is a paper, an open access paper that's quite detailed. It explains the idea behind the project, why we're doing this, how it's set up, how it's designed, what kind of challenges we see, what the use cases are, and so on. So you can look this up through the DOI link on top of the slide and read through the whole thing at your own pace. One thing in the paper, this is part of the motivation. This shows why it's very important to optimize the software that you use for the CPUs on which it will be run. In this case, we're looking at GROMACS, and we see a speed up of 57%. That's quite a bit by properly optimizing GROMACS for CPUs that have AVX512 support. If you're not doing this and you're using a generic binary that basically runs anywhere, you can see you're getting a big decline in simulation speed. And this is typically something that people do when they use containers and the container image. They build one image that works everywhere, which is very nice, but they usually overlook or just ignore that they're actually sacrificing performance by doing that. And with Easy, you're actually getting the best of both worlds. You can go anywhere and still use the same software, and you don't lose the performance aspect. Also, on a bigger scale, we did also with GROMACS a small test on the Yusuf system in Jülich, so where Bernd is located. We did the GROMACS simulations of up to 16,000 cores, and we saw the same scaling behavior with the GROMACS installation we have in Easy compared to the local one that they have on Yusuf. It's actually a little bit better if you look closely, or well, it's probably not statistically significant, but it's certainly competitive with what the local installation is doing. And this is just something we did in Easy. This was not optimized for Yusuf specifically at all. It's a GROMACS installation that works anywhere, but it looks like we've done everything right to get very good performance even on a big scale. Also in Azure, then with a different software package with WRF, so this is weather simulation. They've done the Azure team themselves did some experiments with Easy and using the WRF installation available there. And also there, they saw very good scaling on their cloud environment. So those are just examples that the performance that we get using these installations that we provide can be very good. The last slide is just a bunch of links. So there's lots of information available. There's a website, the documentation. We also have a dedicated Slack channel for Easy, which you can easily join if you're interested. You can keep an eye on our Twitter feed, which is not very active yet, but that's probably going to change soon. And I definitely recommend to take a look at the paper that we have or the recorded talks that we had at the latest EasyBuild user meeting on how to get started with Easy, or specifically how to use WRF in the Azure cloud. Now, maybe Bernd, you can tell me how I'm doing on time.
Yeah, so you kind of used up your time.
Okay, yeah, then I guess I'll skip the demo, or maybe I'll run it in the background while you take care of questions. So I guess
okay, we can. So first, thank you very much, Kenneth, for this quick overview about all this work. I know how hard it is to talk about work which is going on for decades. And what was very nice, and I think most everyone here enjoyed it. And we have a few interesting questions actually. So we have first one from Esteban. How is the interaction between EasyBuild and provisioning tools to automate cluster installation?
The interaction between EasyBuild and provisioning tools. So I guess you mean things like Ansible and these configuration managers, things like this. Yeah. I would say there's definitely interaction possible. So we do see people that run EasyBuild and Ansible playbooks, for example. So EasyBuild is a tool to do individual installations, let's say. If you want to use it to install a whole software stack with it, so let's say thousands of installations, we do have some things that help you with that, but maybe you can use some kind of wrapper around that to make sure everything is consistent. There have been talks at the EasyBuild user meeting of how people are combining EasyBuild and Ansible, and other people are definitely combining it with other tools as well. So there's definitely some possibilities there.
Okay, the next question: how do you tackle heterogeneous clusters? In our countries, I think Esteban means Latin America, but I think it's also true for Europe, smaller sites. It is usual to have very different nodes, and compiling in the head node is not enough. Sometimes you should have applications compiled in different subsets of nodes.
Yep.
Yes.
And essentially what we do in Ghent, and what we also see lots of other people do, is basically have a separate software stack per type of cluster. So if you have an AMD Rome cluster, an Intel Haswell cluster, Intel Skylake cluster, you're basically building the software 3 times. So for each type of cluster, you have a separate software stack. That's one thing. Then of course you need some kind of scripting, or well, ideally you want people to automatically get the proper modules for the hardware that they land up on. So if they get a job running on the AMD system and they do a module load of TensorFlow, let's say, they should get the installation that was optimized for AMD Rome. There's different ways of doing that. You can mount the software stack differently depending on what type of CPU you're on. You can do something with a profile script that basically does a small detection. Oh, this is an AMD system, so I'll use this part of the available modules. And there's different options there. And this is also something we do in EasyBuild actually, where we just have the same software installed multiple times. Different generations of Intel, different generations of AMD. Also for ARM and Power, we basically have the same things multiple times. And we have some detection that does this automatically and easy. So that's something you can see here when I do the sourcing of the init script. One thing this init script does is detect what type of CPU you have automatically. So you don't have to tell it this is an Intel Haswell. It knows how to figure that out. And based on that, it will use a part of the software stack that is specific to that CPU. So you can see it will pick up the modules that are for Intel Haswell. And then when you do a module avail for GROMACS, for example, you can see you're getting the GROMACS installation that's optimized for Intel Haswell. So, and it's really the same thing on a local system. You can do something very, very similar, where you basically, let me show you here by just looking at what's on the file system. You can see we have separate directories for different generations of AMD. And then in here, you have the modules and the actual software installation. Same thing for Intel. We have Intel Haswell and Intel Skylake. And then for ARM, you have a similar structure here, different generations of Graviton and something generic that works anywhere. So you're basically building different software stacks for different types of CPU.
I also remember that EasyBuild had some way to run the EasyBuild command in batch script, so you wouldn't run it on the head node, but basically on the cluster nodes.
Yeah, that's true.
Yeah, and so it had like two advantages. Like once basically you compile the software on the nodes which you really want them, and secondly you could kind of parallelize it, yeah, by basically farming out the building.
Yeah, indeed. So you can EasyBuild has a --job option, which essentially you have to configure it a little bit, but you have to tell it has to talk to Slurm. When you tell EasyBuild, please install TensorFlow and all the dependencies it has, and you combine that with --job, EasyBuild will create a different Slurm job for each of the dependencies. Also set, so separate jobs for all of these things, set dependencies between them, so the jobs are being started in the correct order. And then depending on how many things still need to be installed, you'll get a certain number of jobs, let's say 10. When those 10 jobs are finished, you actually have the installation ready in place. And if you then do the same thing on the different types of clusters you have, you can very easily install the same software on multiple different clusters. Since EasyBuild takes care of all the automation for you, you don't have to worry about putting things in the right place.
Okay, Esteban, happy with the answers? More questions? No. Okay, then we have another one sent in by Liliane, but I guess it might be already have been answered by a slide which came later. How does Singularity and other container solutions fit into Easy?
Okay, that's a good question. So in general, like I mentioned, using container images, you're sort of cutting corners. So you're building one container image that works anywhere. And even that's actually something that will no longer work, or at least will not easily work in the future if you start having not only Intel and AMD CPUs, but you also have ARM CPUs, you have RISC-V CPUs. You cannot really get away anymore with one container image because you have x86 binaries are useless on an ARM system, on a RISC-V system. So that's no longer going to work. But it's even worse than that. If you have one binary to rule them all, you're basically making sure you're not using any of these fancy instructions, AVX2, AVX512, which means you're losing performance. So that's a bad thing. Now, in the Easy project, we do use containers, but for different reasons. Whenever we install software to add it, well, I should say build software to add it into the Easy repository, we do this with what we call a build container. And the main reason for that is just to shield us away from whatever operating system we're running on, whatever cluster in Jülich or in Ghent, or it doesn't really matter, which may be configured differently. We don't want to see all those changes, and that's why we do the build in a container environment. But the actual installation itself, like it is available in Easy, like I was running TensorFlow here, basically works anywhere. So it's not tied to that container anymore. You don't need any containers. So the idea of the compatibility layer we have, this middle layer, and I can actually show this a bit here, I think. If I load, let's say, a GROMACS module, I look where it is. This should somewhere be a pretty deep path. So again, optimized for Haswell, some version of GROMACS, and this is the actual binary. If I look to which libraries this thing is linking, you can see it's not really linking to anything in user-lib or user-lib64. It's picking up everything from EasyBuild itself, including libc. So we're using the libc from our compatibility layer, not the one that's available in the operating system. And this is why the same installation for Haswell can work no matter whether you're using Ubuntu or Fedora or any other operating system. So this is sort of the same idea as you have in containers. If you're running software in a container image, you're using the libc from the container image, not the one from your host. So we're stealing some ideas there in some sense, but we're not contained in the container image. That's a good thing. If there's GPUs available on your system or a fast InfiniBand network, we have direct access to that. And we're not stuck in a container and we have to break out of it somehow to get access to these fast resources. So that's a good thing. So containers are too static. Container images are too static, and this is a way more dynamic environment where you can add software. It just automatically becomes available. You don't have to do any updates. Things just happen more on the fly, on demand. It's a way more dynamic environment.
Okay, I have a kind of related question. So I can see basically how you prepare and the software for the different CPUs. But how do you do it for the networks, for MPI? Do you kind of basically have like when the MPI packages built on all the different hardware, like InfiniBand, OmniPath, whatever,
yep.
or how do yeah?
That's a very good question. And for this, we're mostly relying on the newer libraries like UCX and libfabric, where MPI basically sits on top of. So we build UCX in a way that it has support for InfiniBand and whatever other fabrics are supported by it. We also build OpenMPI with libfabric, and that then farms out to other fabrics like Omnipath or things like this. And this is a pretty recent capability in MPI libraries that makes this possible. So we're basically not taking care of it ourselves. We're relying on the libraries that support this to do it for us.
Oh, so you don't need like special UCX versions, but you can build UCX that it builds multiple underlying networks at the same time. Okay.
You can have a fat UCX library that supports many things.
And then basically when you run it, kind of it detects what network is really there and does the right
it does an auto detect. Now, what we also definitely want to support is that you bring your own MPI library. So we're aware that vendors have their own very tuned MPI installation. And let's say that's an MPage library. We want to make sure that if we provide software installations on top of MPage, a standard MPage, as long as that's ABI compatible with what the vendor provides, you can plug in the vendor provided library. So even though we build on a standard one, as long as it's API compatible, we want to be able to plug that in and get better performance that way. We've done some experiments there, and we're essentially plugging some holes in Easy to make sure you can do that. But we need a bit more experience to see how well that works. But that's definitely something we're keeping in the back of our heads.
Okay, so I don't see any more questions.
There's a raised hand.
Yeah, but I think it was Esteban. And you want more? Okay, Esteban, go ahead. You can unmute and ask yourself.
Yes, hello. Thanks, Kenneth, for your talk. Was really interesting. I think a lot of people will see after this we publish this recording, so it's going to have an impact later also. So I was wondering about how do you manage to benchmark the installation? I mean, usually you have a cluster, you have a set of nodes, and you start a new version of some things, maybe drivers, maybe the application. Do you have some interaction with a way of keeping this information, of benchmarking, some automatic way of doing that?
Not yet, but that's definitely one of the ideas we have in the Easy project as well. Now, many people are interested in this. So for example, if you run GROMACS and you get the simulation speed of 1 nanosecond per day, is that good? Is that bad? Like, how do you tell, right? So you need a reference to other systems. We haven't really seen people publishing numbers like this for their systems yet. And we think that part of the reason is that people are running different software stacks on their system. So something that's very tuned to their system. And maybe they're scared that if we say we do 1 nanosecond per day and the other guys are doing 10 nanoseconds per day, that will make us look bad. So there's definitely something like this going on. With the EASY project, since we have a central software stack and it's being used all over the place, so whoever wants to use it, it's taking away one of these factors. At least they're using the same software and only the system itself is different. And maybe that opens the door to start sharing these numbers and start comparing systems and how they are doing for GROMACS and other software as well. So we hope that EASY can actually enable this. And we're also working and talking to the Reframe developers about this idea of building a shared, like EasyBuild has easy config files, but then test files that you work on together as a community and that you can easily get running on different systems. And also, like I mentioned, another thing we hope that will be possible is that when we publish numbers, for example, for GROMACS, and we say we're getting this kind of performance on this kind of system that has this type of GPUs and CPUs and this much memory and all of that. We hope we can get some feedback from the software developers themselves and say, wait, you're only getting 1 nanosecond per day. That's way too low. So something is wrong in your installation. And maybe we can work together to figure that out. And again, because you have a central software installation stack in EASY, it could be fixed in one place and a lot of people would benefit, which is very different from just fixing it for Ghent and then it only helps people in Ghent. So we think it opens up possibilities to work closer with software developers as well. So yeah, hopefully
that's really clear. Thank you.
Yeah, hopefully EASY will enable this type of stuff.
Thank you.
Any more questions? So while Bernd checks that, I just want to make it clear that people understand what I'm doing here. I've been running some of these examples. You can run these yourself as well. So this EASY demo is a GitHub repository that's available on the EASY GitHub. So if you look for it, EASY demo, you will find it. It also has scripts to do the installation of CVMFS on a Ubuntu system. So you can basically check what's in the script or just run the script if you trust it. It will do very basic stuff like installing CVMFS and configuring it. And it's a 10-line script. You can easily figure out what it's doing. When I'm running all these examples like this open foam script, well, this is a bit of a mess, but let me show you the TensorFlow one. So this is very short. It's just loading a module, running a Python command with a Python script. Now, this TensorFlow installation is not actually on this VM. It's actually sitting in the EASY repository. And as soon as you load the module and start running the Python command, CVMFS will download all the files that are needed to be able to run the simulation. And it's all fully transparent. So you don't have to tell it, oh, I want to use TensorFlow, so please download it first for me. No, it notices that you're trying to access those files. They're not available yet. It just downloads them on the fly and then starts running that thing. So this means if you have thousands of software applications available in your CVMFS repository and EASY, that means you can use them anywhere as long as it's a compatible system, basically any Linux environment. And that's a very, very powerful concept, I think.
Yeah, I guess everyone is looking forward that like we have a supported project for that, and we will hear much more new and interesting things coming out of the EASY project.
Yeah.
We actually have one more question. Eugenio is saying he has noticed that you use like open source software and tool chains for the software. But in your experience, is there really a significant gain from using Intel compilers and libraries in in your experience?
That's a good question, and it's a difficult one to answer. The easy answer is it depends. So definitely historically for Fortran software, there could be a bit of a benefit in using Intel compilers with the Fortran Intel compiler. Now that's actually changing a bit with Intel One API. They've essentially switched to something that's based on LLVM, and they're redoing their Fortran compiler sort of from scratch. So how that will perform or performs currently, I'm not really aware of. In practice, I think there's There can be some benefit by using other compilers, but there's other aspects that you should take care of first. So make sure you're actually using software that was optimized for the CPUs that you're running on, that you're using the proper libraries, that you're not overlooking things like I/O aspects running in the right file system, using the right libraries to make sure you get the best out of the fast interconnect like InfiniBand that you have. Look at those kind of things first before you start playing with different compilers. Because I can tell from experience, switching between compilers is usually not a walk in the park. If it works with GCC, and you try using Clang or the Intel compiler, it's not unlikely that you'll run into compiler errors that you have to figure out first. So it's definitely a very time-consuming thing as well. And yeah, depending on, I guess, on how big your simulations are you really interested in the 5% speed up from using a different compiler or not? So yeah, there's definitely a lot of impact there, especially for Fortran. Also, I think for C++, I think Clang is doing quite well compared to GCC there, but it depends a lot on the software that you're using and building.
Yeah, in our experience in Jülich is the same. It very much depends. We've seen some packages where Intel, especially like MKL or Intel MPI, performs better, but we have clearly seen other cases where whatever MP or Open MPI work better, or some public domain LAPACK library or something. So it always, it depends on the use cases, and we've seen in things in both directions.
Yeah. And there's no clear winner for compiler or MPI or LAPACK or BLAS. It all depends a lot on the software that you're using. Okay, so we are already over 1 hour, and so thank you very much for joining us, and thanks again, Kenneth, for this really interesting talk. I guess you will get even more interest now, and potentially people using it, and even more people at some point even hopefully contributing to EasyBuild and Easy. Let me quickly make an announcement. So like I said, this is a whole series. Will continue in 1 month from now. In 21st of September, we have another webinar lined up. This time it will be about interactive high-performance computing with JupyterLab. Again, please follow us on our RISC2 social media channels, or look at the RISC2 website. And everyone registered, of course, will soon receive information about like where you can download like the slides which Kenneth used today, and when the recording is available. So thanks again, everyone. Thanks again, Kenneth, for this really interesting talk. And see you in a bit. Thank you. Bye-bye. Thank you very much for having me. Bye-bye.